Good morning. I will start in a minute or so. Share screen. Yeah. Good morning, everyone. And this is where we had stopped last time. We are considering an example, and that in example N1 and N2 were at a fixed time point T were defined appropriately, something which survives up to time T and not so. And N1 plus N2 was equal to N. And we had found that this N1T and N2T, they are having independent random variables with Poisson distribution. Today, we will look at what is called conditional variance. So some of these things, significance you will see later. Probably one could have done it when we did conditional expectation. But anyway, it doesn't matter. So let X and Y be continuous random variables such that X has finite second moments. We can even consider these things to be discrete random variables. Actually, in the cases we consider, Y might even be discrete. So maybe one can even modify this. X is a continuous random variable, Y may be discrete or continuous. Anyway, it doesn't matter. Both can be discrete, both can be continuous, one of them discrete, one of them continuous. It doesn't matter. Only thing is, in general case, one has to perhaps bring in measure theoretic notions and things like that. So modulo that kind of an understanding, it can be anything. So we know that for any fixed Y, the conditional probability density function, that is F given capital Y equal to little y. So as a function of little x, so x going to Fx given capital Y equal to little y is a probability density function as a function of x, sorry. It's a probability density function as a function of x. Therefore, it makes to talk about variance or any moments with respect to this probability density function. And basically, conditional variance is going to be variance with respect to this probability density function. Yeah, please note it down if you want. Okay. So the conditional variance of x given y equal to capital Y equal to little y is defined as the variance with respect to that conditional probability density. So if you have to define variance with respect to this density function, in the definition of variance, the expectation, the appropriate corresponding expectation would feature. And we know that conditional expectation of x given capital Y equal to little y is the expectation with respect to this density function. So conditional variance of x, the random variable x given capital Y equal to little y is defined by this formula, that is expectation, rather conditional expectation of x minus that conditional, that expectation of x with respect to that PDF. And the whole thing, you take the square and take the conditional expectation of this square random variable given capital Y equal to little y. If you want to express that as a density or integral with respect to this density function, then it would be, as you can guess, integral over R little x minus conditional expectation x given capital Y equal to little y, the whole squared, fx given y equal to y dx, y equal to little y dx. Okay, if you want to note down anything here, please do. And the definition is here. So since we assume that x has finite second moments, so this has finite second moments, and this is a number. Since little y is fixed here, this conditional expectation of x given y equal to little y is a number which depends on little y. So therefore, this whole thing squared that has finite expectation, that is this quadratic expression, that random variable has a finite expectation. Consequently, the conditional expectation of this random variable given y equal to little y makes sense, that exists. So which means the conditional variance of capital X given capital Y equal to little y makes sense, or it exists. Yeah, please note it down. So this object is a real valued function of little y. So now what we are after is to define conditional variance as a random variable, just like we had done conditional expectation. So to that end, this is a small exercise, very easy, that conditional variance of x given y equal to little y is equal to conditional expectation of x squared given y equal to little y minus this constant, which is the expectation of x with respect to the conditional density of x given y equal to little y. So therefore here this is a constant, so this square. This is what you would expect to see from our experience with random variables earlier and so on. So now note that this is a function of little y. And of course, this is also a function of little y. And we know that the conditional expectation of a random variable which has finite expectation given y equal to little y, that considered as a function of y is a nice function in the sense it is a Borel measure. So the first object here as a function of y is a Borel measurable function on the real line. Now similarly, conditional expectation of x given y equal to little y is also a Borel measurable function of little y. And consequently, the square of that function is also Borel measurable. Consequently, both the objects on the right side of this equation are measurable functions. That is, each of them is a random variable, can be considered as a random variable appropriately. Consequently, that is the case with the left side as well. What I said now, I have just written down here. For these things, you can see our notes, earlier notes. So same thing. The left side is also as a function of y is a nice function. Therefore, the random variable, please note it down. Yeah. So the random variable conditional variance of x given y can be defined on the basic probability space by this recipe. That is conditional variance x given capital Y evaluated at a point omega in the sample space is conditional variance of x given capital Y equal to little y if y omega is equal to little y. The same way we had done it earlier in the case of conditional expectation as a random variable. So that random variable naturally is called conditional variance of capital X given capital Y. So that previous exercise interpreted as for random variables, that is this equation. The random variable conditional variance of x given y is the same thing as the random variable conditional expectation of x squared given y minus the square of the random variable conditional expectation given y. We know from our discussion on conditional expectation, this is a random variable, and this is a random variable. So a small result. This is usually called conditional variance formula. If you want to note it down, note down anything, please do. Yeah. This is called conditional variance formula. So let x and y be random variables such that x has finite second moments. then since x has finite second moments, variance x exists. Variance x, this is a number. Now, just now we have defined the random variable variance of conditional variance of x given y. So it makes sense to talk about expectation of that random variable. So therefore, this is also a number, real number. And we already know conditional expectation of x given y is a random variable. Therefore, it makes sense to talk about variance of that random variable. So this result says variance of x is the sum of these two guys. Yeah, x and y can be discrete, continuous, or general random variables. Only thing is, only stipulation is that x has finite second moments. Okay. So we just now noted that both the sides on the right side are meaningful. So proof. Now in an expression like this, if you start from the left side, we may not know how exactly to proceed to get this. So one starts from the right side. So verify that the first term on the right side, we analyze now. So that is, we just, the variance, conditional variance of x given y. So treating this as the random variable, and this is same thing as expectation of conditional expectation of x squared given y minus the square of conditional expectation x given, and the expectation of the whole. This first quantity here is a random variable. This is also a random variable. So one takes expectation. This is justified by the previous that expression. And I leave it to you to verify that this guy is precisely this one, what we have written. This, the verify that applies to here also. Here also you should see what is the reason for this.
So,
yes,
as we know, expectation of x given y, so this can be proved from there, right?
pardon?
I mean, expectation of conditional expectation is expectation x, right?
Yeah, correct. So you are right. Yeah, that is the kind of reason I want you to supply here. Okay, so you got it. Very good. Yeah, the expectation of the conditional expectation is the expectation of the random variable. Correct. You are absolutely right. Good. See, many of the things which I say, verify that. If they are fairly simple steps only, I will not give the step. If it is slightly more complex, I will give you at least some part of the reason and then ask you to verify. My only this thing is that don't try to read these things just like a storybook. And in mathematical subject, that may not be advisable at all. Except when you are trying to browse through something to get a feel of what it is all about. The nitty-gritties have to be checked. Right. So now the second step, second term, this one, we look at. And similarly, this is again, you chase the definition. This is conditional expectation of x given y is a random variable. Variance of that random variable, you have to define it this way. And once again, using the reason you gave just now, this follows. Add these two expressions, you get what you.
Sir?
Yeah.
Yeah, this expectation x given y will be function of a small y, right?
Which one?
Expectation x given y.
Expectation x given y, you are talking about the random variable, right?
Yeah.
Yeah, random variable is a function of y.
So the second expectation will be with respect to small y, right?
No, see, this is this is a random variable. Okay?
Of small y.
Not small y, it is a random variable.
Okay.
See, this you define at a point y as it there is the conditional expectation of x given y equal to capital Y is also hiding there. This is a composition of two functions. Okay, one function is the y and another is the conditional expectation function. See, go back. Yeah, like this. Okay, so this is, if you want to write it precisely, if you call this function, this is a function on the, as a function of little y, it is a function on the real line. It is little y going to some number, that function. We had called it in our earlier discussion as m of y. When we did conditional expectation, go back to that notes, that is that Poisson processes 1. There, forget about variance here, conditional expectation, that this thing, once you observe that it's a function of little y, you call that function as little m at y. So this, when you define like this, it is little m composition y. Okay, it's a composition of two functions. One function that is from omega to the real line and to the real line. From omega to the real line is the y function, and real line to real line is this m function. It is the little m composition y. You go back to the notes, these symbols also we have used. M composition y and things like that. Or there maybe might have used this thing as the conditioning, this thing as the x. So you will find that. It is a composition of a random variable and a function on the real line. And that function on the real line turns out to be a nice function. That is what we meant by saying that these are Borel measurable. So that composition also becomes a random variable. See, if it is not a nice function, then you, by composing it, that it may, you cannot say assert that resulting composition is a random variable. Okay. Many functions which you encounter ordinarily, continuous functions, differentiable functions, piecewise continuous functions, these are all nice functions. That is, they are all have this property, Borel measure. I mean, measure theory to some extent sort of unifies that kind of things. That is the advantage of measure theory. I mean, that is one of the advantages of measure theory. Okay.
Yes, sir. Thank you.
Yeah. So expectation of the conditional expectation is expectation of X. That proof you go through again. You will see some of those ideas become more apparent. Yeah, please note it down. All right. Now there is another type of objects, random sums, which you will see again. Let ZY, Z1, Z2, Z3, etc. be a sequence of IID one-dimensional random variables. All these things are IID independent random variables. All of them have the same distribution. So let n be a discrete random variable, which is independent of all these guys. These guys may be continuous or discrete, but we are going to assume that n is discrete. Not only that, n takes value in 0, 1, 2, etc., non-negative integers. And let's say P sub capital N at J is the probability mass function of this capital N. Okay. So we are now going to define a random variable X, which will be a random, sum of a random number of these Zi's. And how is that random when you add that comes up? That is through N. In the sense, X is going to be defined as 0. See, this capital N takes value 0, 1, 2, etc. So whenever capital N takes the value 0, X omega is 0. If capital N at omega is K, then this will be Z1 plus Z2 plus Zk at omega. So this kind of a random variable is called a random sum. It is a sum of a random number of random variables. We have already seen one such example, right? Can you recall? Okay. this object inside this bracket, all these guys are random variables. And I going from 1 to n at t. So this is random. So what we have seen, that random variable whose expectation we were computing in example 1, that is a random sum. Yeah, that is of this form. Remember that that n at capital T is a random variable. There's actually n at capital T at omega and things like that. So as this object X is a sum of a random number of random variables, it is called a random sum. We will soon see there will be more of such objects. So this thing, we generally denote it like this. See, remember, even in the example 1, it was like that. It will be written this, though we say I going from 1 to n, even it is I is 0, then you have to interpret this as 0. You have to interpret x as 0 whenever this n is 0. So this kind of a notation, you always keep in mind that is when capital N is equal to takes the value 0, this is to be interpreted as 0. Yeah, please note it. So n and this is as above. X is a random sum given in terms of this random variable n and these guys. So we have now looked at conditional variance, etc. So you can easily see that this kind of a thing makes sense. So conditional variance of x with capital N given to little n is this. So here this right side is a function of n, namely this little n is hanging around here. And also find variance of x. So by using the earlier part of our discussion today, you can find variance of such random sums. And note that example 1, the object we saw in example 1 is an example of a random sum. And we shall stop here for the day. So it's somewhat of a shorter session. These notes will also be put up on the Moodle hopefully today. And next week we will start with something new. So if you have any clarification, if you want any clarification or you want to look at any of the earlier slides, please tell me. I'll be happy to do that.
One quick question. Will you put up a problem set also today?
Problem set to this time I may take a few days.
Okay.
Yeah. That generally I try to do that, but there are occasions when one will be lagging behind. Sometimes problems may be spanning 2 such uploads. Okay. If you don't have any other question or comment, we will stop sharing. And by the way, we'll also have to talk about our midterm exam dates and all that. So be prepared with some. I think that thing given is some the week starting 14th of March or something like that.
Yes, 14th to 18th.
Yeah, so we would like to have it in the first few days of that week. So perhaps for a Monday during the class hour, meaning Monday or Wednesday. So you can have that in mind. I will try to put up formal this thing about those things so that people can think about it or fix and can fix it soon. Yeah. So we will end the session now. And okay, take care and see you next week, Monday. Yeah, thanks a lot.